Thank you everyone for attending today's Foxconn Quantum Computing seminar. Today we have the pleasure of having Yunchao Liu, who will tell us about learning quantum states prepared by shallow circuits in polynomial time. So Yunchao is a postdoc fellow in the Harvard Quantum Initiative. He received his PhD in computer science from Berkeley, and he was advised by Umesh Bazirani. Before that, he completed a bachelor's degree in the Yao class at Tsinghua University. His research focuses on quantum information, computation, and complexity theory, emphasizing the theoretical foundations of quantum computational advantage on NISQ and early fault-tolerant devices. So Yunchao, the floor is yours.
Thanks for the kind invitation and introduction. Hello, everyone. So it's my pleasure to give this talk here. And I will actually talk about two related works on learning shallow quantum circuits and quantum states prepared by shallow circuits in polynomial time based on these two papers. So our goal today is very simple. I want to show you some new techniques that we developed to solve these problems. And actually, they can really be described in this very simple picture. So before I start, I want to say that if you have any questions, please feel free to interrupt me at any time. Okay, so the techniques that I will show you are called quantum stitching. And it is really about efficiently reconstructing a quantum many-body system from local pieces. And as we will see, it is essentially a quantum version of this picture shown on the left-hand side. Okay, so let's start by introducing these two fundamental problems in quantum complexity theory and quantum learning. So here is the first problem, learning shallow quantum circuits. So here we imagine that we are given access to an unknown constant depth quantum circuit U, as shown on the right-hand side. And our goal is to develop a learning algorithm to learn a constant depth quantum circuit that is close to U. So imagine that we can perform some experiments by preparing some input states and measuring the output. And based on these experiments, we want to figure out what is the circuit diagram. And here is the second problem, which is learning quantum states. So here, it's a bit different because here we are just given copies of a specific unknown quantum state, psi. And this quantum state is prepared by some unknown constant depth circuit U. And our goal is also different. Our goal is to learn some constant depth circuit that just prepares this specific state psi. Okay, so in this talk, we will show polynomial time algorithms for solving both problems. And here, let's start by assuming that the system of interest is defined on some finite-dimensional lattice. And we will also maybe mention more general geometry later. And these algorithms also works for slightly higher circuit depths, up to polylog n, and with the cost of a quasi-polynomial running time. Okay, so any questions about these problem definitions? Okay, so now I'll briefly discuss what's the key technical challenge when trying to solve these problems. It's really about efficient reconstruction. So all of the algorithms that we will see today actually all follow a two-step procedure. Step one is to learn local observables for the unknown quantum system. And step two is to efficiently reconstruct a quantum circuit from the learned local observables. So step one is easy to do using standard techniques such as classical shadows. And moreover, because the underlying quantum system is a shallow circuit, we can also argue that actually these local observables will be sufficient information for us to reconstruct the system. So the challenge is really all about step two, which is having these local observables. Can we actually efficiently reconstruct a quantum circuit from the learned local observables? And this is actually a highly non-trivial problem. And the goal of this talk is to tell you about some new and simple techniques to do this. Okay, so let's start with learning shallow quantum circuits based on this joint work. Again, here we are just given access to this black box U, and this black box, we promise that there is some underlying shallow quantum circuit that implements this black box. And our goal is to develop a learning algorithm that interacts with this black box. And eventually, we want to learn a shallow circuit to implement U. And actually, the experiment that we need to perform are all very simple. We only need single qubit random input and output samples. And more specifically, all we need to do is to prepare some random single qubit stabilizer states. And we send it into the black box. And then we measure the output states in a random Pauli basis. So this is also known as the classical shadows for quantum circuits. And using this information, we can efficiently reconstruct all the local interactions of this black box. And next, I will tell you about this theorem, which is we give a polynomial time algorithm for learning shallow quantum circuits from these random input-output samples. Okay, so to begin with, we will review a very basic property of shallow circuits known as light cones. So here is a basic picture, which is a circuit diagram of a shallow circuit. But of course, here we have sort of switched the input and output. So here the input is at the bottom and output is at the top. In previous pictures, it was from left to right. So now it's from bottom to top. And the light cone property says the following. So let's consider a small region A, for example, on the finite-dimensional lattice, on which our quantum system lives on. And here in the picture, we just have a one-dimensional lattice. And we know that each input qubit in A can only affect the output qubits in the light cone of A. So here the light cone is precisely the quantum gates colored in blue. So if we look at the two input qubits in A, if we change the input, it can only affect the output reduced density matrix of the 6 output qubits on the top of the light cone. Any qubit that is not in the light cone will not change due to the effect of A. Okay, so this light cone properties follows from the structure of shallow circuits. But then a naive thought is that maybe we can try to undo the blue gates. If we somehow know what the blue gates are, then we can just undo them and remove these gates from the unknown circuit. And then the underlying circuit U will be acting trivially on the system A. And then it's a shallow circuit on the remaining qubits. So then we will basically solve the problem by iterating this procedure because we simply have a smaller circuit and then a smaller circuit and then again. But of course, we cannot do this because we don't know what the blue gates are. So we cannot directly remove it. So here is a basic idea. Since we don't know what the blue gates are, maybe we can try to guess a small circuit like the green in order to disentangle the region A. And then after coming up with this green circuit, we can sort of then test whether A was indeed disentangled. So let me describe this more formally. So we call this idea a local inversion, which is to guess a small circuit like the green one to disentangle the region A. So how do we do this? Well, because the green circuit is very small, since the light cone is local in this shallow circuit, so we can simply enumerate all of the small circuits. And for each one of them, we can simply imagine applying it, and we test if the action on A becomes identity. That is to test if A is disentangled from the remaining system. Okay, so can we use this to solve the problem? it turns out that, if we can imagine doing this over and over again, maybe there would be a way to reduce the system size. But there is a big issue, which is the small circuit, like the green one that we apply, could be different from the actual light cone, which is the blue. So even though perhaps we can apply this green circuit and disentangle the region A, what we applied is not necessarily canceling with the actual blue gates, because there can be some other arbitrary small circuit that just happen to disentangle the region A. In other words, instead of removing some gates from the system, we're actually adding more gates. And in particular, even though we could potentially disentangle the region A, it could create a mess on the remaining qubits. So in more technical terms, the circuit complexity on the remaining qubits could blow up. And if we just simply iterate this procedure, there will encounter some inevitable difficulties later on. Okay, so maybe this is a little bit hard to understand, but that's completely okay, because I will just tell you what's the idea that allows us to circumvent this problem in the next slide. But any questions so far? Okay, so let me tell you the key idea to address these issues. So I will tell you a 3-step procedure where we want to introduce a new ancilla qubit and swap with the disentangled qubit A1 and then undo the local inversion. Okay, so it's a 3-step procedure called disentangle, swap, and undo. So let me just show you how it works. So our starting point is the same picture as before, right? So here we have on the left-hand side, a unknown shallow circuit U, and then we have a local inversion V1 on top of U. So we have the guarantee that if we apply this local inversion V1, it will achieve the effect on the right-hand side, where the action on A1 becomes identity, which is just looks like this wire in blue. And then there is some unknown action on the remaining qubits. Okay, so this is very simple. Use a small circuit V1 to disentangle the qubit A1. But because of the issues we just discussed, the problem is that U prime could be a lot more complicated. That's the issue. But now we will just see how to get around this issue by the following 3-step procedure. Okay, so the first step is to introduce a new ancilla qubit. Actually, we will just add a wire B1 on both sides. So this looks like very simple and not doing much. And now the second step is we want to actually add a swap gate on the 2 qubits A1, B1. And again, this doesn't look like much has happened, right? But finally, we will do this step 3, which is to undo the local inversion that we applied in the beginning by applying its inverse. So we will apply V1 dagger. Okay, but now if we look at this picture, it still looks like we almost didn't do anything, because if we didn't have this swap operation, then we are just applying some unitary V1 and applying its inverse, which cancels with V1. So it's, in other words, literally nothing has happened. But because of this swap operation in the middle, now something interesting has happened. Because if we look at the very last picture, it looks like the role of A1, B1 have been exchanged. So in other words, the final picture actually is equivalent to this new picture, where the input to the circuit effectively becomes B1, and the wire A1 is literally not doing anything, right? So this is sort of not hard to see. Okay, but what have we accomplished so far? If we summarize everything that we have done so far, it's in sort of this picture. So we have learned a unitary, let's call it W1. So this W1 has three parts, some local inversion, some swap, and the inverse. And we know that this learned unitary W1 achieves the effect shown in this picture, where if we apply W1, it sort of achieved the effect of swapping an input qubit. So in the new picture on the right-hand side, now the ancilla qubit B1 becomes the effective input, and the original input qubit A1 is disentangled. Okay, so we sort of have learned a circuit acting on top of U that achieves the effect of swapping an input wire. And this is very interesting because if we look at the system on the right-hand side, it looks like the system is not disturbed. And this means that we can sort of repeat this procedure for every qubit. And actually, I claim that this idea actually works. And using this idea, we can actually learn the description of a circuit W acting on 2n qubits. And this circuit actually implements the function U dagger tensor U. So this is sort of interesting because we have learned a circuit diagram that simultaneously implements the original unknown shallow circuit U and its inverse U dagger. Okay, so let's see how this works. So let's start from the same picture. We have this small circuit W1 on top that swaps an input qubit. But now, because the system is not disturbed, we can sort of apply this procedure for every qubit. And what will happen after this is that every input qubit is sort of exchanged with a new ancilla qubit. So the overall system looks like this. Very funny picture where the input completely comes from some ancilla system, and the original input now becomes a single wire. But now, if we do a swap operation on top of everything again, it becomes this, right? So again, summarizing everything we have done so far, we basically have learned a 2n qubit circuit W that satisfies this very interesting procedure, where we have a unknown shallow circuit U on the left on the A system and a bunch of ancilla qubits on the B system. And if we put this circuit W on top of everything, it achieves the right-hand side, where the system A becomes ancilla and the system B becomes the unknown shallow circuit U. But this precisely says that W equals U dagger acting on A tensor U acting on B, which means that we have learned a circuit to solve this, to reconstruct this unknown shallow circuit system. So to summarize the key idea, it's really about trying to disentangle a local region without disturbing the system that allows us to repeat for every qubit. Okay, so any questions so far?
Just out of curiosity,
Yeah.
because you're talking about qubits, but if I had qubits, it still works. Does it?
Yeah, it's the same thing because no matter what is the local dimension, we can just the only thing we need to achieve. Yeah, the only thing we need to achieve is this this picture where we find a small circuit to locally disentangle a single local system. So as long as the system is small, no matter whether it's qubits or qubits, it's all the same.
Right. Thanks.
Okay, any other questions? Okay, so now I will address a final point. So one thing that you might be wondering is that we sort of have done a lot of things in this new circuit W that we learned, right? So we sort of did a lot of procedure, try to disentangle each of the qubits. And maybe the question is whether the reconstructed circuit W is still shallow, or maybe W has a lot of circuit depths. Okay, so now I will tell you how to reconstruct this circuit in low depths just by smartly rearranging the terms in W. Okay, and I will tell you this example in 2 dimensions. So here we have this picture which illustrates a 2-dimensional system. And we sort of divide this 2-dimensional system into different regions with 3 colors, red, green, and blue. And this coloring is very interesting because if we look at each individual region, such as a small green region, then every small green region is sort of far away from every other small green region. They are separated by some distance. And similarly, every red region is also separated from every other red region by some distance, as well as the blue. And using this coloring, we can sort of manage to reconstruct the circuit that we described before in low depths. So let's imagine doing the following in parallel for all the green regions. So first, let's imagine applying a local inversion operator for all of the green regions in parallel. So, in order to apply a local inversion for a small region, we have to act on a region that is slightly bigger than the green in order to invert it, right? Because of the light cone structure. But since all of the green regions are far away from each other, so we can sort of do this for all green regions in parallel without interfering with each other. Okay. So now, remember, we need to swap each disentangled region with new ancilla wires. And now we imagine that the system has the following structure where every qubit, like the black one, is connected to an ancilla qubit, like the red one. So all of the swap operations can be done locally using this architecture. And finally, we just undo the local inversion operator by applying its inverse. All of this can be in parallel for all the regions in green color. And similarly, we can continue doing the same thing for red and blue. And finally, swap all qubits with ancilla again. And that's it. This is sort of a way to really efficiently reconstruct the shallow circuit in low depths. Okay.
Excuse me.
That's
I have a question. So for your 3 colors, does it mean that green colors, it doesn't entangle with the red and blue?
Right. So
like for each color, it's only locally entangled within itself. Is that the assumption?
Okay, so, well, not necessarily. So, I mean, overall, we just have a shallow circuit acting on everything, right? We have a shallow circuit that acts on everything, including the red, green, and blue. So there can be local entanglement within each region, but there can also be entanglement across each region. But the magic is that as long as we do this, as long as we do this reconstruction procedure, somehow it will just work, even though there is some entanglement locally everywhere. So all we need to do is to do this swap operation for every qubit. And this color is just telling us what's the order to do this. Because we can do all the qubits with the same color at the same time.
Okay. And another question is that does the width of the green square matters? Does it have to be bigger than the width of the red rectangle?
Yeah. That's a great question, because as you can see, if the green one is too small, then the red one will be touching with each other, and that's not allowed.
Okay, I see.
Right.
Okay, thank you.
So actually, the green one is designed to be big enough to separate the red one.
Okay. Okay, thank you.
But just to clarify, I mean, you can shrink all of them together, and that is kind of what you want to do, so that the regions are small and you can learn them quickly, right? Because you want to guess the unitaries associated with each of them.
Yeah. Yes. Right. So yeah, I mean, we can imagine that each of the small color is just a constant size, but we need to choose the constants carefully in order to separate these red ones. Yeah, so imagine maybe the blue is like 20 by 20, and the red is like 10 by 15 or something.
So just to clarify, so if you give me any 2D example, I can always just do it this way by the way that you have colored the regions, right?
Yes, yes.
But so is there any particular reason why there's 3 regions? Or could you just do a more?
Right, okay. So first of all, our goal is to use as few colors as possible, because the more colors we have, the higher circuit depths we have for the reconstruction, right? So, and actually 3 is the smallest number of colors that we need for 2 dimension. And in general, we can do any dimension, and the number of colors is number of dimension plus 1.
I see. Thank you.
Great. Any other questions? Okay. So yeah, thanks for the great questions. And let's move on to the second problem, which is learning quantum states prepared by shallow circuits, which is based on this following work with Zeph Landau. And here, actually, the situation is quite different. So here, we'll imagine that we are given copies of a quantum state psi. And we know that this quantum state psi is prepared by some shallow circuit U. But we are just given this specific state psi instead of giving access to inputs and outputs of U. Okay, so the only thing we can do is basically to measure this state psi. And our goal is to learn a shallow circuit to prepare psi. And similarly, here we actually only need single qubit random measurement samples in a random poly basis. So this is just the classical shadows for quantum states that allow us to reconstruct all the local observables for the unknown quantum state. And based on these random measurement samples, we can give a polynomial time algorithm for learning quantum states prepared by shallow circuits. Okay, so next I will tell you this algorithm. It's actually very different from the one that we just saw, but it shares some similar spirits, as we will see later. Okay, and our starting point is the same basic idea of local inversion, right? So here, on the left-hand side, we have our unknown quantum state psi. And a local inversion is just a small quantum circuit, like the V1, such that if we apply it, it will disentangle one of the qubits, meaning that one of the qubits is inverted to the state 0. And the remaining qubits are just in some other unknown state. Okay, so from this basic idea, the question is what to do next. And again, there's a similar issue, which is if we just directly apply a local inversion, V1, and even though we have successfully removed one of the qubits, the problem is really that the remaining state phi could be a much more complicated state than before. So in other words, there can be some circuit depths blow up, and this will create a lot of troubles if we try to iterate this. Okay, so next I will tell you the idea that we have to get around this issue. And actually here, it's only a 2-step procedure, which is just local inversion and undo. There's not even a swap operation. But let's see how this works. So, okay, so in this picture, we have an unknown quantum state psi. And this picture is just a sort of a one-dimensional quantum system. And we have this region A, which is a small constant size region. And the first thing we can do is to apply a local inversion V to invert the region A. So here we have, after applying this local inversion V, the qubits in the region A all becomes the 0 state. Okay, but actually step 2 is just for convenience of later discussion. So we are not actually doing anything here. So in step 2, we imagine that we replace the qubits in A, which are already in the state 0. But here we still imagine replacing these qubits with fresh qubits in the state 0. Okay, so this is not doing anything. But then in step 3, we actually undo the local inversion by applying V dagger. Okay, so now you might be surprised because in step 1, 2, 3 overall, we are actually literally not doing anything because all we have done is to apply some unitary and its inverse. Okay, so what's the point? Well, let's look at this picture more carefully, right? And the first observation we can make is that if we look at this picture overall, actually the overall states did not change, right? So we start with some quantum state psi at the bottom, but after doing step 1, 2, 3, we still have the same quantum state psi. But of course, that's sort of a trivial statement because we didn't do anything overall. And now we can also have a new observation too, which is we could argue that we have learned a small part of the state. Because if we focus on a very small piece, let's focus on a very small subset, A0, within A. Then if you look at A0, we can argue that we have learned a circuit for the reduced density matrix on A0. So if we want to prepare the reduced density matrix on A0, we just need to use the green circuit, which we call the backward light cone of A0. So basically, we start from the fresh qubits in the 0 state, we apply the small green circuit, and we trace out some qubits outside 0, and then we have the reduced density matrix on A0. Okay? And this just simply follows from the fact that we have disentangled all the qubits in A, and then we are applying a circuit on top of it. So the qubits inside of A is reconstructed by our new circuit. So we can argue that we have learned a small part of the state. Okay, but still, this is still sort of relatively trivial. But then something interesting happens if we combine the two observations. What we mean is that, combining the two observations, we can say that we have reconstructed a small part of the state without changing the state at all. So we have applied V and V dagger, and we argue that we have constructed a very small part of the state in A0, and overall the global state is not changed, does not change at all. But then we can sort of philosophically wonder that, if we can do something good that doesn't change anything, then why not repeat? Okay, but still, if we can sort of, first we can sort of naively repeat this in parallel on different regions like this, right? So this picture is doing nothing more than just repeating the previous procedure, but independently on many different places. And here we can sort of argue that we have reconstructed part of the states, which are the green regions on top, right? So for each of the so for these qubits and simultaneously with these qubits and these qubits and these qubits, they are all reconstructed by the green circuit, which is the backward light cone of these qubits. But have we successfully reconstructed the entire state? Obviously not, because there are still some regions that we don't know how to reconstruct, right? So the problem is, what about these regions? that's sort of on the edge between the things that we know how to reconstruct. And this is really a fundamental issue because we couldn't possibly cover everything at the same time. Okay. And again, the idea here is that still, after all of these things, the state did not change at all. And maybe we can just repeat by doing another layer on top of this. Okay, but now this gets a little bit complicated because this is now the, the process of reconstruction. By repeating another layer on top of the first layer. And now this gets a little bit complicated, and there could be some potential issue, which is the new layer could even mess up with what we had earlier, right? Remember what we had earlier was that, we argued that for these qubits, we can reconstruct them because of the circuit in the backward light cone. But now we had done something on top of it. And now these qubits lives here, and it's sort of unclear what's going on anymore. So, okay, so what's happening here is that if we imagine actually doing all of these things, maybe we, instead of doing something new, maybe you could even mess up with what we had before. Okay. But it turns out that actually this picture solves the problem. And we claim that we already reconstructed the circuit for the original underlying unknown state psi. And let's see why this is the case. And to do this, actually, we will do something very brave, which is we will attempt to reconstruct the entire output state at once via the global backward light cone of all the qubits. So remember, even though this picture is very complicated, there's one thing we know, which is the state did not change. And what that means is that if we look at the qubits that lives here, right, the qubits lives on the output layer, and we know that the state here is the underlying unknown state psi. And because we have this reconstruction process, maybe we can try to trace the backward light cone of this state on the top and see what happens. And actually, this is what happens. So the backward light cone is simply coloring every qubit on the top by green color. And then imagine that the green color is sort of spreading backwards. And what happened is that some of the spreading process is stopped due to the fresh qubits in the top layer. But some of the spreading process continued because there are some wires that goes from the top all the way to the bottom. But nevertheless, the spreading process will continue for a while, but then still completely stopped by the fresh qubits at the bottom layer. Okay, so this is very interesting. And we can argue that, overall, the green circuit is the reconstruction for our unknown quantum state because that backward light cone, which is the green color, stops entirely at fresh qubits. Okay. So just to be more precise, how exactly do we reconstruct the unknown state psi? Well, we just do the following. Right? We prepare a lot of states in the zero states, and we just implement the green circuit. And somehow, there are some extra qubits that we have used in the process, which we have colored in red. But there's one thing we know, which is after everything, the state that lives on the top is the state psi. Okay, so this looks a little bit magical. And as you can probably feel at this point, the fundamental reason that this works is because there is a sort of a careful geometric arrangement that allows us to completely stop the spreading of the backward light cone using fresh qubits. And this geometric arrangement is what makes this reconstruction successful. Okay, so Okay,
Can
so
I
the
just
only
ask-
remaining thing, yeah.
So I just wanted to ask, so when you go to like 2D, you're going to get 3 layers now instead of 2, and you go to 3D, you'll get 4 layers and so on?
Basically, yes.
Yeah, okay.
That's a great point. And okay, so the only remaining thing is to tell you how to get this, geometric arrangement in general. But we have already covered all the key ideas. So any questions about this? Okay. Okay, so maybe just to clarify again. So, psi is sort of a n-qubit state that lives on top. But you can sort of see that we have used some extra qubits like the red ones. So these ones will just be thrown away after we implement this circuit. And because psi is a pure state, so we sort of know that these ancilla qubits in red must be disentangled from the state psi. So they are just some garbage that we throw away after this reconstruction process. Okay, so finally, I will tell you about how to get this geometric arrangement. And we call this a covering scheme. A covering scheme is just a way to divide a lattice system into layers of subsets with 2 properties. The first property is that subsets in the same layer are sufficiently non-overlapping. And the second property is that subsets in different layers are sufficiently overlapping. And this is very interesting because, in this picture, I have shown many different subsets like the red circles. And we can see that the different circles in the same layer are sufficiently non-overlapping, meaning they are far from each other. But different subsets, you can see that the first layer and the second layer are sort of sufficiently overlapping. So this is actually the property that we require in order to make the reconstruction process work. And how do we achieve this? And actually, it was pointed out already that we probably need 3 layers, and that's actually indeed the case. And our starting point is actually the same familiar picture that we have seen a little while ago, where we have this coloring that divides a 2-dimensional lattice into 3 colors, red, green, and blue. But if we look at this 3 coloring, there is sort of a layer of red colors and a layer of green colors and a layer of blue colors. And they satisfy property 1 because different regions with the same color are sufficiently far from each other. But they do not satisfy property 2, where we demand that different layers are sufficiently overlapping. But actually, the observation here is that, if we look at the red, green, and blue, there is still some space between them. We can sort of make every small piece a little bit bigger, such that they are still separated from each other, but now there is some overlap. And this is precisely what we do like this. What we do is to simply take the previous coloring and grow each of them a little bit. Now, they are still sufficiently separated, but have some overlap across different layers. And this is the idea that finally solves our covering scheme. Cool. So any question about this? Okay, so let me conclude this part with a final remark, which is the connections to condensed matter physics. So in condensed matter physics, there's this notion of phases of matter. In particular, the trivial phase is sort of defined as quantum states prepared by a constant depth circuit on a finite-dimensional lattice. And what we have shown is basically saying that quantum states in the trivial phase can be learned efficiently. And we can also turn this learning algorithm into a testing algorithm. So the corollary is that for an arbitrary state, we can sort of efficiently test whether it is the trivial phase, meaning it has low circuit complexity, or it is in the topological phase, meaning it has high circuit complexity. So our learning algorithm is sort of also an efficient way to test quantum circuit complexity. Okay, so that's all for my technical descriptions. And any questions about these results so far?
So just for the learning, I guess you would try to learn it and then take your learned state and then do a swap test or something, and then if it swap test is always passing, then you've learned the state. Otherwise,
That's
it's topological or something.
Yeah, that's a good idea. And another way to think about that is basically if every step in the learning algorithm can succeed, meaning that whenever we want to find such a local inversion, we can always find it. Then that actually gives you a proof that the quantum state overall is low depth because of the reconstruction argument.
But like, don't you need to? I guess you need to know the depth in order to set up your light cones and stuff.
Yeah.
But I guess you could start assuming the depth is 1 and then keep increasing it.
Yeah.
But you have to this just gives you a proof that the depth is not, anything you tried. Yeah, okay.
Yeah, but technically our problem is to test whether the depth is like less than 10 or like above 1000. And you can sort of efficiently test that. Cool. So any other remarks? Okay, so let me maybe just say a couple more words. So one thing is that so far all of our discussion is sort of assuming that the quantum system that we're trying to learn lives on some finite dimensional lattice. So the question is, can we also do this more generally? And actually, for the first problem of learning shallow quantum circuits, we can sort of do arbitrary, we can sort of learn arbitrary systems as long as the circuit depth is shallow. So even if there is some long-range connectivity, that is still okay. But for the second problem, learning quantum states, there has to be a good covering scheme that we can construct on the underlying geometry. And sort of, it's unclear whether that can be achieved for more complicated graphs beyond lattices. And another feature about all of these results that we talk about is that they all require ancilla qubits. So in both learning shallow quantum circuits and the second task of learning quantum states, the reconstructed circuit both have to use some number of ancilla qubits. And an interesting technical question is, is there some efficient way to learn these systems where we demand that the reconstruction cannot use any ancilla qubits? I think that's probably a hard problem in general, but we can sort of, maybe I can show this. So what we have in the first paper is that in 2 dimensions, we can do this without using any ancilla qubits under some additional small requirements. And this sort of follows a key idea, which is specific to the 2-dimensional geometry, which is, we can sort of cut a 2-dimensional system into 2 halves by doing something in 1 dimension, right? Imagine cutting a system in the middle using like a stripe or something. But that 1-dimensional system can be efficiently found using some dynamic programming algorithm. So overall, we can sort of do this in 2 dimensions, but it's probably hard beyond that.
So I have a question about the ancilla. So like
Yeah.
I mean, you basically trace out the ancilla and still get a pure state at the end. This
Yes,
means
yes.
there shouldn't be any entanglement, right? Between the ancilla. So I mean, isn't this like, yeah, I mean,
I mean, okay.
what's the limitation?
I completely get what you are saying. That's precisely the difficulty, actually. So suppose in general, I gave you a quantum circuit acting on some system qubits and some ancilla qubits, and imagine that this circuit is shallow. And now I tell you that the output state is some pure state on the system qubit and tensor product with the state on the ancilla qubit. And now the question is, can you still prepare the state without using any extra ancilla? That actually is probably hard in general.
I mean, there's this what is it, catalysis or something? But there usually like the ancilla is like a resource state, right? Not like the all zero state. And
right. Okay, so this is sort of a very deep question. And what I can say is that, so I'm not an expert on this, but apparently in condensed matter physics, there is a family of states called invertible states, where people believe that if you have some ancilla qubits, they can be prepared in constant depths. But if not, they must require a lot of circuit depths. So these are sort of these examples which are probably very deep.
okay, thank you.
Yeah, so that's, I mean, we spent a lot of time trying to understand this issue as well, but it just seems very deep. Okay, so let me just conclude by mentioning some general remarks. So what we have discussed today is two new learning algorithms based on quantum stitching of local inversions. And these algorithms work in this simple and clean settings of learning shallow quantum circuits. And this is very different from what people do in the standard variational quantum algorithm literature based on gradient descent. And the interesting question is, can this be the basis of efficient learning algorithms in more general settings? And maybe we can use these techniques to construct more provable quantum algorithms for NIST devices. And of course, for these things, we need to deal with more practical issues such as noise. But here we can use quantum error mitigation because all we need for the learning algorithm is to use local observables. And we can use quantum error mitigation to get error-free local observables. And maybe that could be a way to reduce noise. Okay, so that's all I have. Thanks for your attention.
Yeah, thank you very much. Yeah, it was a very wonderful, very informative talk. Yes, I think we have maybe just a few minutes left for some questions, if you want to keep under an hour. So yeah, go ahead.
First of all, I'd like to say thank you very much. That was an extremely clear, very nice talk. Thank you for that. I wonder if like in the first protocol where you're learning UDAG tensor U,
yeah.
Do you think there might be like more efficient ways of learning just U itself and not having to use like 2n qubits? And I'm
That's
sure
a great
you've thought about this a
question.
lot.
Actually, yeah, that's a great question because, you know, this reconstruction procedure, one of the shortcomings is that it has to use n ancilla qubits. So we start with our unknown circuit is just n qubits, but the reconstruction uses 2n qubits. Okay, and as I mentioned before, for quantum systems on 2 dimension or less, there are ways to, I think, avoid using any ancilla qubits. But in general, it doesn't seem like this is possible.
Okay. I have one more question, but maybe I'll give other people a chance. Okay, I'll ask my question. So you didn't really mention how you guess and the cost of guessing.
Right.
Like you know, you confined it to a small piece, and then you didn't really talk about how hard the small piece is, and how it scales in the size of the piece.
Yeah. Okay. So great question. So first of all, we should clarify that all of these things actually we're just imagining doing them, but in reality, all of these are just classical post-processing because all the quantum experiment is just collecting the random input and output measurements. But having those random samples, we can sort of efficiently reconstruct the local interactions, meaning if we have something here, then the output here. So all of these local input-output relationships can be efficiently reconstructed. And now we just imagine literally enumerating over everything here. So if the circuit depth is d, then the size of this is sort of d squared for this one-dimensional system, right? And we just try everything in each case, and that could be exponential in d squared. So in general, it's just exponential in the circuit depths.
Right. So you're like doing a covering of the space of unitaries and then checking every single one,
Yeah.
seeing what's the best.
Yeah.
Okay.
Yeah, but of course, if you assume that the underlying circuit comes from some like Clifford plus T, for example, then that would be much easier.
Great. Thank you.
Right. So we have time maybe for one more question from someone else. Okay, if not, I actually wanted to ask something sort of maybe not so related. I'm just wondering, like, so from what we learned about this, the learning the quantum states, like using this kind of reconstruction, does it have some implication on like the marginal problem? Does it tell me that, if I know certain marginal states of some particular global states, then it uniquely specifies it? Is there some implication like that?
Yeah. So, okay, great question. So in quantum complexity theory, there's a problem called quantum marginal problem, which is, suppose I give you a list of density matrices. Can you tell me whether these density matrices comes from a specific global state or not? Meaning that is there a state that is consistent with all of these local reduced density matrices versus not? So this problem is actually in general QMA hard. But for quantum states prepared by shallow circuits, there is a lot of structure. In particular, we know that, even before we have a learning algorithm, we already know that as long as you give me the density matrices, then that uniquely determines the global quantum state. The question is whether we can efficiently reconstruct the state from these local reduced density matrices. And that's what sort of our reconstruction process solved. Yeah.
Sorry, where do we know this unique reconstruction result from?
I guess that's sort of Brooke law, but it's basically, just because the circuit is shallow. Yeah. If you'd like, I can sort of maybe spend 30 seconds to describe the argument. So it's sort of saying that, these states, you can write down a Hamiltonian with a spectral gap such that these states are the ground states unique ground state of a local Hamiltonian with a spectral gap. And now, as long as you give me reduced density matrices from the states, I can sort of measure the energy of these reduced density matrices, right? And that sort of uniquely determines the state.